am Dr. Pavitra Bharadwaj. I am Associate Professor in the Department of Computer Science in the Jesus and Mary College of University of Delhi. So friends, we have been discussing a wide variety of topics related to the operating system in the past few lectures, and you would be fascinated at the enormous amount of work the operating system does in the background, which we don't even realize as the users of the computer system. And sometimes we feel that all the work that we are seeing is being done at the front end, but actually more work is being done by the operating system at the back end. So we have been talking about process management and process synchronization, how processes are managed, they are created, they are executed, and they are terminated. And we have been talking about how different processes can be synchronized, what different mechanisms the operating system uses for synchronizing different processes. Now, when we are talking about multi-programming systems, so one very important function which the operating system takes forward is the scheduling of processes, which is known as CPU scheduling. So, how processes will be assigned CPU and how the CPU will be taken back from the processes is also a very important factor, a very important feature in the operating system's dynamics. So, today's lecture, this talk is going to be concerned around CPU scheduling and how processes are scheduled in a CPU. So, basically CPU scheduling is the foundation of any multi-programming operating system, because by switching the processes amongst by switching the CPU amongst different processes, the operating system will make the computer more productive. Now, at the end of the thing, the end goal of the operating system is to to facilitate resource maximization. So, all the resources of the computer system have to be used to their optimum, to their maximum, and the operating system always thrives to achieve this function. Whether those resources are the memory, whether the resource is a CPU, or whether it is any other resource of the computer, the ultimate aim of the operating system is for maximizing the utilization of the resource. So, when we are talking about CPU, again the same thing applies, that if we have a single processor system, so then only one process can run at a time, and all the other processes, they will wait until the CPU is free and it can be rescheduled. But multi-programming operating systems or multi-programming systems, they run multiple processes at all times. More than one process is running at all times, and this is being done in order to maximize the CPU utilization, because we will see that how the processes execute when they are running, how they execute, right. So, the idea basically is very simple, that a process is executed unless it must wait for the completion of some IO request. We know that all the processes that we are talking about, they have either an IO burst or they have a CPU burst. That is, they keep alternating between CPU and the input output. So, once they start, then they go for input output, then they come back for the CPU, and this process goes on till the time the process terminates. So, every time the process is going for input output, so then another process can be assigned to the CPU, so that the CPU does not remain idle at any point of time. The whole idea is that the CPU should remain busy at all the time. So, when one process goes for its input output, the other process has to be assigned to the CPU. So, if we see that in the process execution, basically it consists of a cycle of CPU execution and input output wait. So, we can say that the entire execution of the process can be divided into two bursts or two phases. First is when it is using the CPU, and the second is when it is using the IO. So, these are known as CPU burst when the CPU is being used, and IO burst when the input output devices are being used. So, basically all processes will keep on alternating between the CPU burst and the IO burst. So, first when the process starts, it starts with a CPU burst. After execution, then it may go for an input output. So, then that is called input output burst. Then it will come back again and it will have its CPU burst. So, it will require the CPU again until finally, when the process is going to terminate. So, when the process terminates, then the final burst is also a CPU burst only. So, it starts with the CPU burst, it ends with the CPU burst, but in between it may go for multiple input output bursts. So, an input output bound program, basically they will have short CPU bursts. So, when we were talking about process mix, in process management, that time also we had said that it is the responsibility of the operating system to create an optimum mix of CPU bound processes and IO bound processes, because when we say CPU bound processes, that processes will require longer CPU bursts, maybe less number but longer duration, whereas IO burst or IO focused processes, they will require multiple, or they will have more of input output requirements, and it will require CPU for shorter durations of time. It may require multiple times but for shorter duration. So, there is an advantage to this also, that when you need the CPU for a shorter time but multiple times, or you need it for less number of times but for longer duration. So, this point we will cover later on when we talk about the scheduling algorithm. So, anyways, the point idea here is that the distribution is very important. That is how this selection is done. That is taken care of by the CPU scheduling algorithm. That is, the right mix of CPU bound and IO bound processes has to be created, so that the optimum mix is given and the CPU is utilized to its maximum. So, if we look at this chart, basically this chart shows the frequency and the burst duration. So, we see that the frequency of low burst processes, that is in time duration, that is much higher than the frequency of those processes which require more time. So, they are less in number. So, basically CPU burst durations are more in frequency than the IO burst durations. So, CPU scheduler, basically the CPU scheduler has the main task, that is whenever the CPU will become idle, the operating system will select one of the processes in the ready queue to be executed. The selection process is carried out by the short term scheduler, or we call as the CPU scheduler. Basically, when we are talking about scheduling here, we are only referring to short term scheduling algorithm. So, what will happen in the ready queue of the CPU, there will always be some processes, and whenever the CPU becomes idle, the scheduler will pick up the process from the ready queue and it will assign it to the CPU. So, this picking up of the process and from the memory and assigning it to the CPU is the primary job of the short term scheduler, or what we are calling as the CPU scheduler. Now, ready queue, what we are saying, it can be implemented using any of the techniques. So, it could be a FIFO queue, that is a first in first out queue, it could be a priority queue, or it could be a tree, or it could be a simple unordered linked list. So, whatever type of queue it is, the scheduler will always pick up according to the algorithm of the queue, it will pick up the process and assign it to the CPU. Now, conceptually, whenever we are saying that the processes in the ready queue, they are all lined up and waiting for a chance to run on the CPU, right? But actually it is what? It is the process control block of the CPU, the PCB of the processes which are in the queue that are waiting for the execution in the CPU. Now, scheduling, when we say, so basically we have to understand that what are the reasons, what are the need, or what are the conditions or circumstances under which scheduling decisions have to be taken. So, first condition under which the CPU scheduling has to be done is that when a process switches from the running state to the waiting state, that is, it is going for an input output, or it is going into a wait state for before termination. Before termination, the process is in its wait state. So either way, whenever a process is, you know, going into the wait state, then the switch has to be done, that is the CPU has to be assigned to another process. Then another circumstance could be that when a process is switching from the running state to the ready state, that is when it is, you know, when an interrupt will occur. So a process was running, an interrupt occurred, and now the process is stopped and it has gone back into the ready queue, and another process has to be assigned to the CPU. So this is interrupt based basically. Or the third condition could be that when a process switches between from the waiting state to the ready state, that is at the completion of the IO. It had gone for an IO, so it had gone into a wait state. Now the IO is complete, so again the process has joined the ready queue, so it is again in the ready state. And fourth condition is that when a process terminates. So once a process terminates, then obviously the CPU is to be assigned to another process. So when we say that these four conditions are there, first condition is when the process is going into a wait state. Second condition is that when the process is, when an interrupt is occurring, right, and the process is switching from one CPU is switching from one process to the other. Third is when the process switches from the wait to the ready, that is after completion, and fourth is when the process terminates. So out of these four conditions, two conditions, that is when the process is going into an IO or when the process is terminating, these are non-preemptive or these are cooperative, because in these the process which was running has been automatically on its own, the process has stopped. But second and third, that is when an interrupt occurs or when a process switches from the waiting state to the ready state, in the second and third condition we say it is preemptive. Preemptive means that some other process is asking the CPU to stop from executing a particular process and go on executing another process. So now we will see what is, you know, the difference between non-preemptive and the preemptive type of scheduling, and we will see different algorithms which are going to, you know, fall into either preemptive or non-preemptive, and some algorithms which can be executed or which can be, you know, implemented using both preemptive as well as non-preemptive strategies. So under non-preemptive scheduling, once a CPU has been allocated to a process, then the process keeps the CPU until it releases the CPU, either by terminating or by switching to the waiting state, right. So the example of this is the older operating systems like Microsoft Windows 3.x, or, you know, operating systems of Mac which came prior to OS X. Now from Windows 95 onwards and after Mac OS X, all operating systems, they are only using preemptive type of scheduling. Why is it so? Because non-preemptive schedulings can be very dangerous. We will see how they can, you know, lead to race conditions, right. So preemptive scheduling therefore is more important and it is more suggestive. Now for example, if we take this example and see that if we have two processes, right, which share the data. Now while one process is updating the data, it is preempted so that the second process can run the run its process, or the second process can start execution. Now the second process then tries to read the data which was actually, you know, which the first process had to change, but because it was preempted, so now the data is in an inconsistent state. Now the second process is reading a data item which is actually inconsistent item, it is not in its correct state. So therefore this is definitely, this preemption of a process is going to cause, you know, race conditions in the system. So there are, of course, you know, solutions to this problem of race condition also, but this is very, very critical. Although in non-preemptive also there can be a problem that, you know, some process can keep on holding the CPU for a very large amount of time, for very long. So then also other processes can, you know, they can go into an infinite wait condition. That also is a problem, but with preemption this problem is even aggravated, that there is a race condition here. Now furthermore, when preemptive scheduling is being considered, it also affects the design of the operating system kernel. When we are saying operating system kernel, we mean that when the processing of a system call is happening, then the kernel is busy with the activity on behalf of the process. Now such activities may involve changing important kernel data, like for example input output queues are there, and if the process is preempted in the middle of this change that the kernel is doing, and then the kernel needs to read or modify the same structure. So therefore this preemption of a kernel process can further lead to more serious problems. So because interrupts which are happening in the system, they can occur at any time. When we are saying interrupt, the definition itself means that it can occur at any time, and because it cannot always be ignored by the kernel. So therefore the sections of the code which are affected by the interrupt, they are guarded from simultaneous use. So therefore most operating systems, they will have to accept interrupt at almost all times. Why? Because if you don't accept the interrupt, then you may lose some input or some output may be overwritten. So interrupt have to be handled. But what is the solution, or what is the remedy to this? That the sections of code which are not accessed concurrently by several processes, those smaller sections can be disabling their interrupts. So no interrupt can enter into those sections which are being accessed concurrently. Once the execution is done, then they can re-enable their interrupt. When the process is leaving, then it can re-enable the interrupt. But when the process enters that section, the critical section, then it may disable the interrupt, so that while the critical section is being executed, no interrupt can stop or preempt the process. It is very important to understand that these sections of code which disable the interrupt, they do not occur very frequently, they occur very rarely, and they also contain very few instructions. So it is only for a very short duration of time that the interrupts are disabled, because as we have already seen that interrupts are very vital for the operating system. If you disable interrupts for a longer period of time, there are dangers that you will lose on some important input which you would be getting, or some output data may be overwritten. So interrupts cannot and should not be disabled for a very long period of time. Then there is a specific module in the operating system which is known as the dispatcher module. Now what is the job of the dispatcher module? That it gives control of the CPU to the process which is selected by the short term scheduler. So basically the main function of a dispatcher is the switching of context, that is it moves the CPU from one process to the other process. So it will involve context switching, it will involve switching to the user mode and jumping to the proper location in the user program so that the program can be restarted, right. So the dispatcher should be very fast, because we understand that the time required by the dispatcher to stop one process and start another process, which is known as the dispatch latency. The dispatcher is also using some amount of time in context switching. So this time of context switching which is taken by the dispatcher, which is known as its latency, it has to be minimum, because you cannot give so much time only in context switching, and the CPU needs to start execution. So every time the context switch is occurring, the processes are switching, the dispatcher has to be invoked. Therefore the dispatcher needs to be as fast as possible. It cannot be a slow functioning module. Now what are the different scheduling criteria? If we look at the scheduling criteria, or what are the different algorithms, they have different properties, and the choice of a particular algorithm will it may favor one class of process over another. So when we are choosing an algorithm, we have to look at a particular situation in which the algorithm has to be applied. So, we must consider the properties of various algorithms before we can use these algorithms for any kind of scheduling processes to be implemented by the CPU. Now, there are specific criteria under which which will help us choose which algorithm is to be required. Now, CPU utilization is of course the primary objective of the entire function of scheduling. So, we want that the CPU should be as busy as possible. So, we theoretically speaking CPU utilization can range from 0 to 100%, but in a real system generally it ranges from 40% in a lightly loaded system to about 90% for a heavily loaded system. So, there are different criteria based on which we will see that what is the utilization of the CPU. How do you measure this term CPU utilization? So, the first criteria or the first yardstick that we use for measuring the utilization of the CPU is the throughput. Throughput basically means that when the CPU is busy executing processes, then work is being done, definitely work is happening. And how do you know that work is happening or work is being done? By the number of processes that are completed per unit time, which is called the throughput. This is same in case of machines also we use this word, that is what is the throughput, that is what is the output which is generated per unit time. So, here also what is the number of processes which are completed per unit time, which is known as the throughput. For long processes this rate may be 1 process per hour, for short processes it may be 10 processes per second. But this again can be contested, because if the CPU is executing one long process does not mean that the throughput is low, because the number of instructions it is executing may be higher. Whereas if it is executing shorter processes, shorter transactions, then you cannot say that the throughput is higher, because again the number and complexity of the transactions is also very important in this. Then we have another yardstick, that is known as turnaround time. Turnaround time means that from the point a particular process enters, till the time the process comes out, that is known as the turnaround time. That is how long it took for the complete execution of the process. That is this interval from the time of submission of a process to the time of completion is known as turnaround time. Now, turnaround time will be the sum of periods which is spent in waiting to get into the memory, waiting in the ready queue, execution on the CPU, and then doing the IO. That is the complete time, that is turnaround time, right from getting into the memory to the time doing the IO and completing is known as turnaround time. Again, turnaround time can be a difficult yardstick because of the same reason, that if the process is a more complicated process, or if it has got much more larger number of instructions or much more larger number of transactions, turnaround time may be much higher. If it is a shorter, simpler process, the turnaround time may be much lesser. So, you cannot really put it as a common feedback. Therefore, another yardstick is used, which is waiting time. That is, CPU scheduling algorithm will not affect the amount of time during which a process executes or does IO. It only affects the amount of time which it spends waiting in the ready queue. So, waiting time is the sum of the periods spent waiting in the ready queue. So, the idea is to have the minimum waiting time for all the processes. So, if a processor gives a minimum waiting time, then it is considered to be a more utilized processor than the one which is having a higher waiting time. Then we have the most appropriate, to an extent, the response time. Now, if you are talking about an interactive system, right, so turnaround time may not be the best criteria, as we already said, because a process will produce some output fairly early, and then it will continue computing the new results with the previous results that are being to the user. So therefore, this measure of turnaround time, as we already discussed, may not be the perfect measure for calculating the the utilization of the CPU. So another measure is what we are using is the time from which the submission of a request until the first response is produced. So this measure is known as response time, and it is only what time the CPU is taking to start responding, and it is not the time it takes to output the response. So turnaround time is generally limited by the speed of the output device, because finally when you get the output, then you are dependent on the output device also. But in this case, when the response time we are only talking about the first response which is given by the CPU. So we will be continuing with our discussion on scheduling algorithms. Till then, keep watching CEC. Thank you.